Hello everyone, and welcome to Introduction to R. In this lesson, we're going to be covering linear regression and how to carry out linear regression in R. Now, in the last few lessons, we learned about statistical inference techniques, including the t-test, chi-squared test, and ANOVA, which let you analyze differences between data samples and populations. Predictive modeling, using data samples to make predictions about unseen data, such as data that has yet to be generated, is another common data analytics task. Predictive modeling is a form of machine learning which describes using computers to automate the process of finding patterns in data. Now, linear regression is one of the most basic predictive modeling techniques that is used for predicting numeric response variables based on one or more explanatory variables. The term regression in predictive modeling generally refers to any modeling task that involves predicting a real numbered value, as opposed to classification, which involves predicting categories or classes. The term linear in the name linear regression refers to the fact that the method models data with a linear combination of explanatory variables. A linear combination is an expression where one or more variables are scaled by a constant factor and then added together. In the case of linear regression with a single explanatory variable, the linear combination used in the linear regression formula can be expressed as this formula I've written out here. So we'll have some response variable, and it will be set equal to an intercept term plus a constant multiplier times whatever the explanatory variable is. So this basic linear regression form can be used to make predictions for any sorts of responses. For instance, if we had data on houses, this response variable might be something like the sale price of a house, and then our explanatory variable could be something like the square footage of the house, or the number of bedrooms, or anything like that that might explain what the sale price was. So the right side of this equation defines a line with a certain y-intercept and then a slope times the explanatory variable. And what the linear regression model ends up doing in its most basic form like this is it will fit a straight line to the response variable, and the line that it fits is going to minimize the squared differences of the line from the actual points. And these differences are called the errors or residuals. We're not going to go into all the mathematical detail or optimizations that can be involved in how you actually go about finding what that optimal line is, but the end result is that you will end up fitting a line to some points that give a best fit to the data. And since linear regression is fitting data with a straight line, it is most effective in cases where the response variable and explanatory variable have a linear relationship. If there's a nonlinear relationship, you might end up with a model that kind of works depending on what it is, but it might not work well in some cases. So to give an explanation of linear regression in R, we're going to revisit the MT-CARS dataset, and we're going to use linear regression to predict the gas mileage of cars based on the weight of a vehicle. So first, we're just going to start by loading in a plotting library and looking at the distributions of these variables with a scatter plot. So let's load that in, and I might have to zoom out a little bit. But we can see that from this plot here, it looks like the MPG, or fuel efficiency, has a pretty clear negative association with the weight. That makes sense. Heavier cars are probably harder to move and then require more fuel to get them to go a certain distance. So heavier cars appear to, on average, have worse miles per gallon. So let's use a linear regression to create a line of best fit to this data that we could potentially use to make predictions on new cars based on their weight. So to define a linear regression in R, you use the LM function for linear model. And then the first argument you pass in is a formula defining what the relation you want to do for the regression is. In this case, we want to have miles per gallon be the thing we're explaining. So miles per gallon is our y variable in this case. So we're putting MPG there. then we do a tilde, and everything after the tilde comes the explanatory variables. In this case, we're just doing a simple linear regression with only one explanatory variable. So we're going to put weight there, and then comma, we pass in whatever our data set is. In this case, our data set is empty cars. So this little line here is all we need to do to create a linear regression of miles per gallon on weight. We're going to save that as MPG model, and then we're going to call summary on the model to pull up some summary data about how the model is fit. So let's run this and look through what the summary output looks like. First, you can see that it shows us what our model was. Then it shows us some information about the residuals. So under the coefficients, it's going to show us what the intercept term is and all of the other coefficients. For this, we only had weight. But it's also going to tell us some information about what the actual coefficient is, what the error is, and most importantly, what the p-value for that coefficient is. So basically, if we have a low p-value for a certain coefficient, it's telling us that for this model, that is a good predictor of what our y variable is. So in this case, our weight has a p-value that's extremely small. It's at the scale of 10 to the negative 10. So that's such a small p-value. It means we're almost certain that weight has some effect on the miles per gallon of a car. And you can also see these little asterisks that are after the different variables. Those just denote whether the different variables are significant at different significance levels. So if you see 3 stars, that means it's significant at a very low p-value. 2 stars is 0.001, 1 star is 0.01, etc. You're basically looking for any variables that have some kind of marker after them, because if they have high p-values, they'll just be blank there. And if that's the case, you can think about maybe taking some variables out of your model. And then we have some other output at the bottom here. There's a couple important things to look at here. We have a multiple r squared, adjusted r squared, and also an overall p-value. What the r squared value tells you, this multiple r squared, it's called the coefficient of determination. It tells you the amount of variance in the y variable that can be explained by the model. So in this case, it's telling us that about 75% of the variance in miles per gallon can be explained by weight, because that was the only thing passed into our model. So 75% of it is being explained by the model. And you'll also note that there's an adjusted r squared here. What the adjusted r squared does is if you have a model with many different variables in it, explanatory variables, it will adjust this r squared value downward depending on how many additional variables you have, because the r squared can only increase as you add more variables. So it's better generally to be looking at the adjusted r squared, because if you make a model with like 100 explanatory variables, you might end up with an r squared that looks pretty high, which means it could be perceived as being a good model. But if it just gets a higher r squared by throwing the kitchen sink at it, but the adjustment is lower, then that might not be such a good model. And generally, you want to use a model that's as simple as possible while also maximizing how well it performs. So you should be looking for a model that gets the highest adjusted r squared value. So now that we've gone a bit into what the output of a linear regression looks like in R, let's go ahead and plot the line that this regression model forms on the scatter plot we made earlier. So this is what this cell is going to do. We're basically just recreating the scatter plot with this, but we're adding a line that's going to take the intercept we found and the slope that we found, and we're just going to color it red. So we're basically just drawing a line on that same scatter plot, and I'll run that and zoom out. So this is a visual representation of the model we just created. So in this simple linear regression form, essentially, if we were trying to predict miles per gallon from weight, we could use this line to do it. You just tell us whatever the weight of the car is you want us to predict on. Maybe the weight is 3. and then you'd go up to 3 on the x-axis, and you just go to wherever the line is, and then you'd read over on the y-axis what's the miles per gallon associated with that. So if we had a car with a weight of 3, which I believe in this might mean 3 tons, it's either that or 3,000, I'm not exactly sure what the units are. The miles per gallon for that looks like it's maybe around 21.5 or so. And that's essentially how you make predictions using a linear regression model. And you'd actually plug the numbers into the formula instead of kind of eyeballing it off a plot like this. But that's essentially what it amounts to. Now, one important thing to note with linear regressions is that outliers can have a very large influence on the outcome of your regression model. So I'm going to add an additional point to this data set that is a substantial outlier. So we're going to add a new car called supercar that's going to be extremely heavy. So it has a weight of 10, which is higher than any of the other cars we've seen. But it's also going to be very fuel efficient with MPG of 50. So this is going to constitute an outlier both in terms of weight and miles per gallon. And after adding this new outlier, we're going to rerun the model and then add a new line to the data and make a new scatter plot. And we'll see that just by adding 1 point to this data, it's going to greatly affect what the model shows us. So let's run this here, and I'll zoom out again. And you can see that our outlier point, let me see, there we go. Our outlier point way up here in the corner, that's only one data point. But just having that 1 point way up there has completely changed our model. Instead of having a line going through most of the points where it seemed like it would create a reasonable prediction for things, the line has been pulled all the way up because it's trying to somehow fit this point way up here. And having points far away from the line for a linear regression model creates very large errors because it's trying to minimize the sum of the squared errors. So the bigger the gap is between a point and the line, that distance is being squared and added to the error. So large differences are magnified even more, which is why an outlier point can be particularly troublesome and make such a big change in the regression output. So it's important to keep in mind that outliers can have such a big effect like this, and just doing things like inspecting scatter plots to see if there are major outliers can help you determine whether linear regression is something you should use, or perhaps maybe consider removing outliers and doing something else with them if you want to use a linear regression model. So after you create a linear regression in R, you might want to make predictions using the model you already made. We kind of gave an example of what making predictions manually just by eyeballing a plot would look like, but that's not what you actually want to do if you're doing it in code. You want to get an exact prediction, and you might want to do that for many data points all at the same time. Well, R includes a predict function that allows you to do a lot of predictions at the same time easily. So let's go ahead and use the predict function. All we're going to do is make predictions on the original data set here using the original weights. But you could use this to make predictions on new cars with weights you hadn't seen in the original data set too. So to make predictions, we're just going to say predict. The first argument we're going to pass in is the model that we created. We stored that as MPG model. And then for new data, we're just going to pass in whatever the data set we're making predictions is. And this is going to be expecting a data set that has the same columns or same variables as the original one that was used to make the model. And after we run this, it's going to save predicted values, and we'll just print those out. So we can see here that in this case, if we were using our model to predict all these different cars, these are what the predictions would be. And if we wanted to, since these are predictions on the actual training data points we use to make the model, we could calculate what the difference or residuals are between these predictions and what the actual values were. All we'd have to do that is take the MPG column, so these are the actual values, and then just subtract off the predictions we made. These will become residuals, and we'll print those out. So just by inspecting those, we get a sense of how far off the predictions were. So for this car, we were minus 2.28 mpg off, and some of them were above, some of them were below. Now, it's important to note that these residuals, when doing a linear regression model, the model assumes that these residuals are going to be normally distributed. If they aren't, it means linear regression might not be an appropriate model for doing your prediction task. So after making a model and being able to calculate some residuals, you might want to investigate whether the residuals approach a normal distribution. One way you can do that is by creating a normal QQ plot or quantile plot. And to do that in R, you can use the QQ norm function on your residuals. So I'm going to call QQ norm on the residuals. I'm also going to call QQ line on the residuals, which will just draw a line at a 45-degree angle through the plot. So we'll run this here. This is essentially comparing our residuals to what we'd expect from a normal distribution. If the residuals all fall on this line, then that means the distribution of the residuals are essentially normal. And the further the points lie from this line here, the further the residuals are from a normal distribution. In this case, it looks like the bulk of our data here does lie pretty close to the normal QQ line. So the residuals do appear to be fairly normally distributed. We do have some data in the tails that are getting further away. So it seems that the prediction is doing fairly well in the middle of the prediction range, but maybe some of the predictions being made at the tails, so for some of the more extreme cars, we might be getting things that are a little bit off of normality. So this doesn't look too bad, but these tails might raise some concerns in terms of whether we might be able to do something that works better than this basic linear regression model. Now, after creating our linear regression model, it would be useful to have some metric we can use to evaluate its quality. We already talked about the R-squared and adjusted R-squared measures as ways to see if the regression model is good. And that's a useful way of testing whether a linear regression model is performing well. But that's not a metric you can necessarily calculate for other types of models that you might want to compare to the quality of your linear regression model. So it'd be nice to have a metric that you can calculate based on your predictions for any different sort of model you might be using, so you can compare across a common metric with your linear regression. So say if you're doing some things with decision trees or random forests or neural networks or something, and those models might not have an R-squared metric you can use, we might like some common metric we can compare them all across to see which one is performing the best. One common metric you can use for looking at the quality of predictions of a regression model is root mean squared error. The name itself kind of says what it is. It is the square root of the average squared differences of the predictions. So basically, if we wanted to define a function in R to do this, we'll say root mean squared error is a function that takes our predicted values and the true target labels. And to calculate the root mean squared error, we just take the targets minus the predicted values. So that is our residuals. We square the residuals. We take the average mean of all the squared residuals, and then take the square root. That will get us the root mean squared error. So we're going to define that function, then we'll run it on our predictions and the actual values, which are in the miles per gallon column. We'll just run this and compute the root mean squared error to show that it does work. So in this case, the root mean squared error is about 2.9 mpg. And it should be noted that the root mean squared error is a metric that depends on the problem you're working with. So this root mean squared error only really makes sense in the context of this problem we're dealing with. If we were working with some other problem with different values for variables and whatnot, this number could be completely different and would have no connection to how good the model is performing versus this one. Now, we went through the trouble of defining a function and calculating the root mean squared error by hand here. But of course, with R, you can load in libraries and packages that can do things like this for you. One package that has a root mean squared error function is called the caret package. So if we wanted to use that and not make something by hand, we could just say library caret to load in the caret package. And then it has an RMSE, or root mean squared error function. And as you can see, the package produced the exact same result that we got. We just were able to load it in and do it easily without having to define something ourselves. So in our first example, we had a pretty good linear relationship between weight and miles per gallon, but variables often exhibit non-linear relationships that can't be fit very well with a straight line. In these cases, we can actually fit curved lines to the data by adding additional higher ordered terms like squared terms, cubic terms, etc. to our model. And then we can run a linear regression that involves those additional higher order terms. A model that includes higher order terms is known as polynomial regression. So I'll give an example of how to include higher order terms and run a polynomial regression in R. So to do that, we will use our linear model function again, LM. We're going to predict MPG again. Again, we're going to use the weight column, or the weight variable, but we're going to add an additional higher order squared term of weight. To do that, we'll say plus, and then we wrap the higher order term in this I function. So we'll say I weight squared. And what that will do is it'll add an additional term for the square of the weight and see if that has any relationship to the miles per gallon. We'll call that a quadratic model because it's including a squared term. So we'll run that and do a summary again. And now we are going to have two explanatory variables. We have the weight variable, the linear weight variable without the squared term. And now we have the squared weight term as well in the model. And we can see that in the output, both the linear weight term and the squared weight term have pretty low p-values. So that means that the model is finding that the squared weight term is actually useful for explaining the difference in miles per gallon, just like the linear weight term did. And you'll also note here that under the adjusted R squared, that's gone up to about 80%. In the original model that didn't include this extra term, the adjusted R squared was something like 75% or so. So by adding in this extra term, we've managed to explain about 5% more of the variance using this new model. So now let's replot this new function against the scatter plot of the data to see how adding this additional term influenced the line we fit. Since we have a squared term here, we're now going to be able to see curvature in the line, and maybe that will allow it to fit the data better. So what I'm doing here is just defining a new function based on the output of our model with the intercept, the x term, and the weight squared term, and then we're going to plot it. So let's just run this and see what the new function is. You can see that instead of a perfectly straight line, since we had a squared term in there, we have some curvature, and it seems like the model here is pretty similar to the straight line for a lot of it, but then at the end it's kind of curving out a bit, trying to fit these points at the end a bit better. And maybe that is resulting in a more reasonable model, because the first one that was a linear model actually eventually was dipping down way below where these points were, and that was maybe making it not get very good predictions on the heavier cars. Now this does look like it might be a better model. Let's go ahead and try to confirm that with another metric by calculating the root mean squared error again. So we're going to make predictions using predict on our new quadratic model. The new data is going to be the same, the data set itself, and then we'll just use the root mean squared error function we made earlier. We'll run that, and we can see that the root mean squared error has dropped a bit. I believe before it was about 2.9 or so, and it's down some. So that leads us to believe that this new model is probably a better one than the last one, because both the adjusted R squared and the root mean squared error have improved. One thing we have to be careful about, though, is overfitting the data. Overfitting describes a situation where our model fits the data we use to create it, known as the training data, too closely, which can result in poor generalization to new data that might lie outside of the points we saw in the original data set. This is why we generally don't want to use the training data itself to evaluate the model or choose which model is best, because it tends to give you a biased an often overly optimistic estimate of the performance of the model. Now, one of the strengths of the simple first and second order linear regression models we've used so far is that they're so simple that they're not very likely to overfit the data very much, because they're constrained to only fitting the data with a line that has a single curve in it. But the more complex the model we create becomes, and the more freedom it has to fit the training data, the greater the risk we run of overfitting the data. For example, we could include more polynomial terms in our regression model to fit the training data more closely and achieve a lower root mean squared error score against the training data set, but this would almost certainly not generalize well to new data. So let's illustrate this point by fitting a 10th order polynomial to our data. So all we're going to do is rerun our linear regression model, but we're going to add a whole bunch of extra polynomial terms. So in addition to the squared term, we're going to add cube term to the fourth, all the way up to a 10th order term. Why do I have an extra plus there? So when we run the model and check the coefficients, we can see that they're kind of all over the place. But let's use the model coefficients to make a function and then plot it. So I'm going to take these coefficients, and I've written them down here in another function that we can plot. So these are all the coefficients that were found from our model. And we're going to plot another line, but this time it's going to be a 10th order polynomial line, so it can have many bends in it. And we'll see that this model ends up doing things that probably do not fit the data well. You can see that it's squiggling around using those 10 terms to try to fit the model, or to fit the data as closely as it can. But to do that, at the end here, it's making a huge curve down and then up, just so that it can fit these last 3 points very closely. This huge dip in the model here, that is almost certainly not something we would want. In fact, in this case, we know this is not even possible because the dip in the line goes below 0. It's not possible to have a car with 0 or negative miles per gallon. So this dip doesn't make any sense in the context of thinking about cars that we're trying to generalize to, but the data set didn't have any data in that range. So as far as the model was concerned, it didn't care about predicting things in that range because there was no data there. So it made this crazy curve just so that the model would have less error on these training points that were way up here. So this is just an example of how using a model that has more flexibility can result in something that is going to lead to bad predictions and generalizations if you end up getting points that are outside of the range of values you saw in your training data. Now, thus far in this lesson, we've only been making linear regression models that deal with a single explanatory variable. We did make some polynomial models that included various polynomial terms of that one variable, but everything was just based on weight. If we wanted to, though, we could make models that include as many explanatory variables as we have. So a model with additional explanatory variables is called a multiple linear regression, and to create one in R, all you have to do is just add other columns to the model you're going to make. So we'll give an example of how to do that just by including an extra column. We're going to make the same model we made in the first place, but we're going to add horsepower. So now we're going to predict the miles per gallon based on both the weight and plus the horsepower column. And maybe adding in horsepower tells us a little bit more about the car. Cars with huge, powerful engines might get really good horsepower, but maybe that means their miles per gallon isn't quite as good. So let's run this and pull up a summary. Again, in the summary output, we're now going to see some data for the horsepower column. And we can see that both weight and horsepower came up with pretty low p-values, so that's telling us that both of these variables were statistically significant for this model. And again, the overall model p-value is pretty low. And if we wanted to, we could add additional polynomial features for both of these variables. And we'll also note that the adjusted R squared here is about 81.5. That's the highest adjusted R squared we've seen so far. It's even better than the polynomial model we made. Now, if we wanted to, we could make this multiple regression into a polynomial model as well by adding in some squared terms for both the weight and the horsepower. So let's see how that would look. If we scroll down, we're just creating the same model of MPG with weight and horsepower, but we're going to add a squared term for the weight and add a squared term for the horsepower. So now we have 4 terms total, and we will run and look at the summary here. So we can see that in this case, all 4 of the different terms came up as being statistically significant, at least at the 5% level. And our adjusted R squared now is 87%. That's by far the highest adjusted R squared we've seen so far. So this might be the best model we've created. We might have to be careful about doing too much overfitting, but that's a good sign. And the root mean squared error is 1.9, which is quite a bit better than the last time we checked root mean squared error for the polynomial model. Also note that once you start working with models that have many different explanatory variables, it starts to become difficult to visualize the results because you can only really easily look at 2 dimensions at the same time. And when you're working with many different dimensions, that's not really something you can do that efficiently. So you start having to rely more heavily on numeric output, like this table here that's showing us the p-values of different things, as well as adjusted R squareds and perhaps other metrics like root mean squared error. Now, to give a final example of a model including a lot of different variables, let's make one last linear regression predicting miles per gallon with every single other variable that's in the whole data set. So if you want to do a linear regression like that, R makes it really easy to do. All you have to do is use the linear model function, pass whatever variable you want for y, we'll do MPG again, and then after the tilde, you just put a period. The period is telling the model, use every single other column to predict with. So instead of having to explicitly include everything, like saying weight plus horsepower plus the number of cylinders plus and having a big long thing, just say period and it's saying we want everything. And that's an easy way to make the big model. And you can even include everything with period and subtract things from that if you wanted to. So let's say we wanted to include every variable but not the weight, we could say minus weight. And that's a convenient way of maybe excluding certain variables that you know aren't going to be useful. For instance, maybe there's an indicator variable column that doesn't really have any predictive power. You could just subtract that off so it's not included. But in this case, we don't have a column like that. So we'll include everything. And we'll make one final summary of this model that's going to have a whole bunch of different explanatory variables in it. So we'll run that. We can see we have a whole bunch of different variables here. And now the p-values for any particular variable are not statistically significant. We'll see even weight that was really strong before, it's pretty close to statistically significant at the 5% level, but it's only coming out as 0.06. And none of the other ones are even close to being significant here. In addition, our adjusted R squared value is around 80.5%. That's pretty good, but it's not nearly as good as the model where we had just horsepower and weight with this couple of squared terms. A likely reason this model is not performing quite as well as we might expect, and we're not seeing many statistically significant columns, is that another assumption of linear regression is that when you're running a multiple regression, the model assumes the variables you're passing in are independent of one another. But it's very likely that some of these columns aren't independent. For instance, horsepower and cylinder, well, maybe those two things are highly correlated because a big, powerful engine with high horsepower is usually going to have a lot of cylinders. So it's likely that we have a lot of columns that are actually highly correlated with one another. And when you do a linear regression with highly correlated explanatory variables, it can throw off the results and result in things like this where we're not seeing any particular column that appears to be statistically significant, even though with a simpler model that only included a couple columns, we did have that. So one thing you can do to try to help with this is before doing a linear regression model, look at the pairwise correlations between the different explanatory variables you have. And if there's some very highly correlated variables, you might want to remove some of those to get rid of the correlation. Or you could try to do some sort of dimensionality reduction technique that combines different columns in some way so that you can eliminate some of this problem. So to wrap up for this lesson, linear regression is one of the most common and useful techniques for making real numbered predictions on data. It's a good place to start pretty much any time you need to be making a numeric prediction, because at the very least, it's fairly simple, tends to run pretty quickly, and can give you a decent baseline prediction that you can use and compare other models to. So if you're trying to do something pretty complicated, say using some kind of boosted decision trees or neural networks, and you're getting prediction results that aren't even much better than a simple linear regression, you might as well just stick with the simple model, because then you don't have to worry about doing anything super complicated. So in the next lesson, we're going to revisit the Titanic disaster survival dataset and turn our attention to the classification task, which is making predictions, putting things into categories or classes instead of predicting real numbered values. And to start with that, we're going to look at logistic regression, which is essentially a transformation of the linear regression we used here, but it allows it to make classification style predictions instead of predicting real numbers. So thanks for watching, and I'll see you again next time.